Now we come back to Bluetooth. Now the Bluetooth is named after the king Bluetooth. Actually his name was not Bluetooth, his name was Harold Blatan, something like that. Okay, Danish king. And but he was fond of blueberries, so his tooth were blue. His teeth were blue. Alright? And why it is named after a Danish king? Because this technology came from that country. Okay? So it originally started with Ericsson. And Ericsson's Bluetooth project in 1994. And what they wanted to do was they wanted to have cell phones talk to each other over short distances. Okay? And then Nokia and other companies joined and they formed a standard body called Bluetooth SIG in 1998. And in 1999 the standard came out. They went to IEEE and got the IEEE seal 15.1 in 2002. But they were not very happy with the time it takes in the standard body. Okay, and this is true. Because if you can have 5 or 6 companies can get together and they can easily make a standard, everybody agrees, no problem, right? When you go to 200 bodies of 2,000 people, there are a lot more divergent opinions and everything takes time. So they came out of IEEE, and so the later versions are handled by the Bluetooth SIG. So 4.0 has nothing to do with IEEE, for example. So the key features are very low power. Now this is by the way version 1.0. So these numbers have all changed. But very low power, 10 microampere in standby. So when nothing is happening, it is taking very little battery. 50 milliampere while transmitting. Now this would be considered, both would be considered very high for today, but it was 1994 and 98 times. $5 per device and 9 millimeter square single chips. 9 millimeter square, you can imagine 3 millimeter by 3 millimeter. You know, it's like less than your nail. That is how they, very small chips can handle the whole thing. So there have been lots of versions starting from 2002. 1, 5, completed 2003, November 2003, and higher variable rate transmission. Also, the SCO is synchronous. Basically, so what happens is Bluetooth has a special mode for audio because phone companies are making it, their main application is audio, right? So they have a special mode, SCO, so they changed that, and then they did adaptive frequency hopping. So as we go into the details of Bluetooth, one thing you will find is that it uses frequency hopping. So we are talking about frequency hopping, where you change the frequency every few milliseconds, and that is what is used in Bluetooth. Okay, you will see that. But they made it adaptive so that if there's interference, you go to different frequencies. 2.0 increased the data rate further, and they started getting 3 megabits using GPSK. So previously, they did tell you the rate, but it was more like 1 megabit and used very simple modulation. Now they went into differential phase shifting. And then they started with video applications, and they, and so on and so forth. 2.1, again enhanced data rate, and then the secure pairing. In the beginning, the pairing was not very secure. Any device could connect to any device. And then they introduced some idea of putting zeros and numbers and IDs and so on and so forth. And now, I mean, like, basically now it is much more convenient and secure, but previously it was not. So they started thinking of secure pairing in 2007, moved on to 24 megabits using Wi-Fi assist. Wi-Fi assist means that you talk in Bluetooth and you tell the telephone, look, I'm going to send you this, and then you send it through Wi-Fi. So that's how they got 24 megabits. 4.0 is low energy. So this is basically IoT time frame. The smaller devices are requiring larger battery life, several years. So they had to create a new file which is totally incompatible with the previous one. And this is called Bluetooth Smart or BLE. BLE is Bluetooth Low Energy. Right? So BLE or Bluetooth Smart. Then 4.1 came about with some fixing to the same things, and then 4.2 has come about, which is larger packets, better privacy, and IPv6 compatibility. Now this smart, actually, so Bluetooth is already, I mean, if you just say networking, Bluetooth is networking, right? So your point is clear that now when we talk about smartness, you're talking about smartness for the Internet of Things, right? So when we say Zigbee is smart, Zigbee designed for Internet of Things. Bluetooth is smart, Bluetooth specially designed for Internet of Things. So that's a good observation that basically smartness, I said that the smartness is moving from computation to storage to communication. Now it is moving to communication at low energy. There are many communication technologies, but we are trying the lowest energy we can do, and if something can do low energy, we call it smart. Alright, so now we have 4.2. We will start with 1 and then jump straight to 4. Okay? We won't do anything in between. So 1. So 1 ran actually in 2.4 gigahertz band. So there's complete 80 megahertz. It uses whole thing, 79 megahertz band. It uses the whole frequency band. Remember, Wi-Fi divided it into 20 they decided 20 megahertz to be used. These guys decided to use the whole 79 megahertz. And which is less in some other countries. But anyway, and they get 1 megabit at the PHY layer, but they get 720 kilobit at the user layer. Basically, PHY layer is where the zeros and ones are happening, but there's a lot of overhead, headers and things like that. By the time it comes to the user gets 720 kilobits. And 1 megahertz means that while they're using the whole band, 79 megahertz, they're using it 1 megahertz at a time. So they just hop. So they're using this 1 megahertz, and they're going to this megahertz, and they're going to that megahertz. So they're using only 1 megahertz, but they're using it all over. Hopping. So they get 1 megabits. And how often they hop? They hop every 625 microseconds. Okay? So 1600 times per second. Security, they use challenge response authentication and 128-bit encryption as a standard. The output power is 20 dBm per 100 meters. They have 3 classes of devices. Class 1 go up to 100 meters. Class 2 go medium. And class 3 go 10 meters. They send 0 dBm or 1 milliwatt. Class 2 send 2.5 milliwatt or 4 dBm. And class 1 send out 20 dBm, which is 0.1 watt. Alright, so obviously class 1 devices probably are not powered by battery because they are giving out 0.1 watt on the air, but class 3 probably are. Okay, and this one shows the frequency hopping. So what I am showing here is 2 different networks in the same room. Are in the same space. So blue network was here at this frequency. This is frequency and this is time. So in this slot, the blue network was here, then moved to that one and it stayed here, and then moved to that one and came back, and then moved here and then went there and moved there. It is randomly hopping. Alright, so there is a random number generator, which both the receiver and the sender know. Actually, everybody knows the random number generator. Everybody knows. Only thing different is the seed. So the seed is different. The seed is known by the receiver and the transmitter. They know exactly that they are going to be moving to. Right? And so these are all random patterns. Similarly, the other network also is following the same random number generator with a different seed. And it is producing different set of random numbers, and then it moves. Once in a while they might collide, but most of the time they're okay. Right, so when you connect, the thing is like this. When you connect, let's say I connect to you, at that time we negotiate all the parameters, and one of them is seed. And then they're connected forever. I mean, the thing is, when say for example you use Bluetooth for headset or something, like when it connects to your phone or when it connects to your TV, at that time all the negotiations are done.
I'm saying, is the patterning of that some function of the speed and the time? Or...
Okay, so you know how the random number generators work. Basically, random number generator is simply a formula. Okay, it could be a very simple formula such as x new is equal to 5 times x old plus 1. That's it, period. That's a very simple, and that's a random number generator. Okay, not very practical, but it will generate random number between 0 and 4. Okay, so you do use that formula, but the thing is, what is the x0? Right? Everybody using x0 will get a different sequence. And then you just put into the formula every slot and you get it, right? But there are certain rules, and you can see that you don't move in certain slots here. So there's a rule here, because in the middle of the transmission you don't move. If you're sending a packet, the whole packet goes at the same frequency. Now, the seeds are actually not designed that way, but you could select, if you're smart enough, you could select, let's say, 10 seeds, which will generate numbers which are not going to interfere much. But I don't think people do that. I mean, in the simulation, we use random number generators in simulation analysis. When we do simulations, we need random numbers. And we use the same random number generators and we use the seeds. There we select 10 seeds such that there is no overlap among the 10 streams. But here there is not much coordination. Yeah, direct sequence is, okay, yeah, it's the spectrum. So the spectrum comes in two ways. One is direct sequence, another is frequency hopping. This one is frequency hopping. If you remember, Wi-Fi did direct sequence and frequency hopping also, right? But we didn't talk about much about frequency hopping. It was not used much. In A, B, C, D, F, G, all of them went into FDM and then never came back, right? So that was an element. Here they started with frequency hopping. So this is not DS. This is not direct sequence. They're not going to make 11 bits out of 1 bit, 11 bits out of 1 bit, nothing like that. But the key new thing that you're learning is, for the first time, you're seeing the frequencies are hopping and how often they're hopping. See, we kept saying few milliseconds, things like that. This is actually 625 microseconds. This is the real. Why do they do frequency hopping?
Because there is no any damage here, like.
Yeah, right. No. So the reason, I think when we talk about frequency hopping, then we discuss this thing. The frequency hopping was invented for military purposes so that nobody could jam. But soon they found it can be used for sharing. Why? Because if we use different seeds, we could all talk at the same time on the same frequency, no problem. Right? So even though there is no jamming is not the issue, but then there is no interference when we are sharing in the same frequency band, actually, not on the same frequency, on the same frequency band. So there are so many, right now, I'm sure that half of the Bluetooth devices are on in this room, right? If there are 16, 17 people, there is 8 Bluetooths going on right now. Other half may be off, otherwise everybody's Bluetooth is on, right? Right. So the thing is, I'm not sure. Okay, so that's the thing is that I am not sure how you decide this hopping frequency. Everything here is come from some analysis. There must be a paper which people did the analysis and said if you have this hopping, what is the positive, what is the negative of hopping much later and less. So here, with 625 microseconds per hop, you might get, when you get interference, the number of bits that are affected is small compared to if you had, hopping every second. Then you might lose 10 packets in a second. Here you lose part of the packet and maybe you make it up somehow through CRC or something. So hopping very slowly will not help much because then you are almost constant. And hopping too fast obviously has disadvantages because you have to reset some things in this circuitry. So they came up with 625 microseconds per hop, and as I said, they don't hop in the middle of a packet. So this hop is less than a packet. you see the packet could be three slots, right? And so clearly they didn't want to hop much slower. If you hop slower, then your whole packet will be gone and you won't notice it. Now you probably will notice some packet part of the packet.